Welcome to the 23rd chapter on virtual substitution and real arithmetic in the Logical Foundations of Cyber-Physical Systems textbook, where we will advance our understanding on real arithmetic from the previous chapter, where we've seen already how we can handle, by virtual substitution, real arithmetic proving for linear and quadratic equations. But, of course, linear and quadratic equations aren't everything. So what we're going to look at now in this chapter is the question how we deal with linear and quadratic inequalities. Virtual substitution is what still will be our main workhorse, where we're pretending to substitute in a generalized expression into a logical formula without literally doing so, but by virtually doing so, because we simply equivalently rephrase each of the occurrences of that. So remember how that worked. For example, instead of substituting in a fraction with a division, we just substitute in something virtually that sort of corresponds to that by already right away multiplying it up. And in a sense, using multiplication instead of division, because multiplication is more harmless, it even works when it's 0. And likewise, instead of substituting in these scary-looking square root expressions, we virtually substitute them in and immediately replace it equivalently by squaring things up, essentially. And now we'll do something like that also only for the inequality cases. We will again work with virtual substitutions to make that happen, but the point is, well, inequalities are more interesting, but also more challenging. And why are they more challenging? Well, because certainly inequalities have a lot more solutions than equations do. So if you write down an inequality and try to solve it, well, depending on the degree of the involved polynomials, you will find 1 or 2 or some number of solutions, depending on the degree of the polynomial. But for inequalities, they have a ton of solutions potentially. They have infinitely many. They even have uncountably infinitely many. We cannot literally substitute them in, and we might even find it challenging to virtually substitute them all in. So we need to become a bit more clever about what we're doing. We still, in order to give back a finite formula for quantifier elimination, to give back an equivalent but quantifier-free expression, we still have to somehow find a finite representation of all the possible cases of solutions, which is going to keep us a bit busy. But the point of today's chapter still is that because cyber-physical systems are so important and require a significant understanding, and because differential dynamic logic proves hybrid systems properties with cyber-physical systems applications, but it does reduce it to real arithmetic, which means we need to figure out how to handle the resulting real arithmetic and prove this too. Now, what are our learning objectives? On the modeling and control side, there again an indirect impact, just like in the previous chapter, that this understanding from this chapter has on CPS models and controls by informing the reader about the consequences of analytic complexity resulting from, different arithmetical modeling trade-offs. Remember, there's always more than one way of writing down a model. There's always more than one way of writing down a property that is, well, for all practical purposes, essentially equivalent. If only we knew what would be better for real arithmetic, that's the thing we would be choosing. In particular, there are quite subtle analytic consequences from different arithmetic formulations for pretty similar questions and have quite an impact on finding the right trade-off for stating CPS models. For example, in practical terms, if you would like the safety distance of your car compared to a stoplight to be good, it doesn't matter a whole lot whether you're stating that the position of your car should be less than the position of the stop car, or whether you're stating that it should be less or equal than the position of the stoplight. Because, yeah, sure, mathematically there's a difference, but in applications, not so much. Because if you're stopped right at the same position as the stoplight, well, that's good enough if you want it to, and maybe also it's bad if you don't want it to, depending on what your arithmetic trade-offs look like. Now, on the computational thinking side, this chapter is a lot more heavy again because we will be looking at rigorous arithmetical reasoning, which is of course completely crucial for cyber-physical systems, and we will look at not just how that can be done rigorously and automatically for equations, but also for inequalities, where again, that's crucial in reality because many properties of cyber-physical systems are stated in terms of inequalities because, well, you worry a lot about distances, being bounded, not too far away, but far enough away, and things like that. That happen rather often. In fact, quadratic expressions happen rather often because often you deal with norms of the Euclidean norm, which is a quadratic expression at the end of the day. Now, we will still be exploiting the logical trinity for real arithmetic because we will still, just like in the previous chapter, exploit the flexibility of moving back and forth between the syntax and semantics of an expression at will. Only now, we won't stop at just moving back and forth the logical trinity by looking at the roots of a polynomial and avoiding the mention of their square roots and divisions as solutions, but we will also do so for points in between to capture the kinds of things that inequalities need as solutions in an exhaustive way. In fact, what we will be looking at is infinities and infinitesimals as the way of going about it. On the CPS skills side, this chapter has an indirect impact on the CPS skills by looking at the pragmatics of CPS analysis for modeling and analysis trade-offs in order to enable verification of cyber-physical systems at scale. What have we seen already? We have seen already the virtual substitution theorem for quadratic equations. So when we have an equality in the middle of our, without loss of generality, remember, conjunctive number of conditions about an existentially quantified variable x. We say there is an x such that ax squared plus bx plus c equals 0 and some other conditions f. That is true if and only if the solution or the solutions for this quadratic equation make the logical formula f happy. And what are the solutions of this quadratic equation? Well, that sort of depends on, for example, whether a is 0 or not, which in general, remember, we can't know because if a is a polynomial term and other variables, not x shouldn't be mentioned in ABC, otherwise it's the wrong shape that we wrote down. But if a is a polynomial in the other variables, then we can't directly easily tell whether it is 0 or whether it might be 0 or whether it definitely isn't 0. So, well, but when in doubt, we can still use logic to distinguish this because we say, well, a is 0, but b is not, and then the linear solution minus c over b is the only solution that this then linear equation admits, and that means the whole existential quantifier is equivalent to the remaining condition f being true for the one solution minus c over b for x that this linear equation then admits, except we virtually substituted. Remember the bar and the red color here indicating that we don't literally substitute, we merely virtually substitute by rewriting the divisions out of the way right away. But that was only one case. Well, the other case was that it's a proper quadratic equation, and that happens whenever a isn't 0, which again, we can't necessarily generally always know, but we can certainly write down or between the two. So a isn't 0, but the discriminant of this polynomial tells us that a square root exists. So the discriminant says that b squared minus 4ac greater than or equal to 0 is true, which means this is a solvable quadratic equation. And in that case, it is equivalent to the remaining formula f being true for one of the square roots. So for either the positive or the negative square root. This is precisely the solution. Minus b plus or minus the square root of b squared minus 4ac and the whole thing divided by 2a. And that means the entire conjunction is equivalent in that case where a isn't 0 to it being true for the positive or negative square root expression. And this square root actually exists because, well, precisely the discriminant said it did. So it's the square root of the real number and not a square root of a negative number. That would give us an imaginary square root. Overall, however, this formula is equivalent to this or that, so this to this disjunction, unless A and B and C are all zeros. In that case, this wasn't a proper, particularly informative expression because, well, now we will have to look through F to find out more stuff. And remember also that the key lemma to make this theorem true is that it doesn't matter whether we use literal or virtual substitution in these cases, in the sense that, well, if we were to use literal substitution, it's sort of kind of obvious where the linear, respectively the two quadratic solutions are the only ones we can have. But of course, these would then be in a very syntactically augmented first order logic, where all these square root expressions and divisions lurk around. But it turns out that the formula where we literally take the liberty of substituting a square root expression such as of the form a plus b square root c over d into for x is equivalent to the case where we virtually substitute it in. So we substitute this expression in and rewrite it right away by getting rid of division by multiplication and getting rid of square roots by squaring the expressions and so on along the way. And then since both are equivalent, that means it doesn't matter which one we mention up here, except it sort of actually does, because if we use the virtual substitutions, the ones with the bars in these cases, then we stay in an equivalence that's actually in the first order logic of real arithmetic, which is of course kind of important to make sure that this equivalence is usable in first order logic of real arithmetic. Anyway, this tells us a whole lot, but it only tells us a whole lot if we find a linear or quadratic equation among the conditions on x. If we do, amazing, we're done. But suppose we don't. What happens if there's only inequalities in this formula? Then, well, if this, for example, would be an inequality, but there's an other equation within f, then, well, we would commute the expression and work with that one instead. But if none of them are, if none of them have any proper equations that are informative, or they do, but they could all be zero, then we have to look through f to find out clever stuff. And that's what we're doing right now. So if we had an inequality, if we had a quadratic inequality, again, x of course not occurring in ABC, we've seen that now, then how do we equivalently rephrase the question that there is an x such that ax squared plus bx plus c less or equals 0 and f is true? Well, still, I guess the whole expression can only be true if f is true for one of the solutions of that. How do you solve a quadratic inequality again? Well, you solve a quadratic inequality by solving the quadratic equality and hoping for the best. So, what are the solutions of these? Well, the quadratic inequality has as solutions whatever the quadratic equality has, which are how many solutions again? Well, 1 or 2, depending on whether a was 0 or not, which we generally can't know. So let's plug this in, right? So again, of course, under the assumption that a, b, c aren't all 0, because then this wouldn't be an informative quadratic inequality. This is equivalent to f being true for the linear solution, in case this was actually a linear inequality, or for one of the two quadratic solutions, in case this was actually a quadratic inequality. Well, hold on a moment. I mean, that sounds fine so far, because certainly the one linear root of this polynomial is a solution in case it was linear, and the two quadratic roots of this polynomial are solutions in case it was really a quadratic and solvable inequality. But these aren't the only ones, right? I mean, there could be more solutions because we're talking about an entire inequality. So yeah, we need to plug other stuff in, which I guess gives us more disjunction somewhere. But what? What are we supposed to do? I mean, f and then the solution. But then actually but then actually this solution plus or minus something. But what? Oh, that's hard. We can't plug them all in. So the point is that we already have the square roots, but we need a solution that's representative for all the other points of the inequality. And one way of making that happen is that maybe the inequality is true for very, 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 very small values. Why small? Well, because it's a lesser equal, so the smaller this thing is, sort of, right, the more true it will be. What small number do we plug in? Minus 100? That sounds small to me. Maybe it's not small enough. Minus 200? Maybe minus 1,000,000? How small is small? It depends on A and B and C and all kinds of things and so on. Well, suppose we were to plug in a really, 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 really small number, minus infinity. That would correspond to plugging really, really tiny little numbers. The only problem is, what is minus infinity? So it's a rubber band number, sort of, that whenever you take it and compare it to another number, it will say minus infinity is smaller than any other number you measure it with. Just like plus infinity is a rubber band number that always is a bit longer than you expect it to be. Whenever you take the plus infinity and compare it to another number, then the infinity says, actually I was a bit bigger than you thought I was. Okay, well, so minus infinity is smaller than all real numbers, and plus infinity is bigger than all real numbers. That's good. But we can't literally mention it. Because minus infinity, well, that's not a real number. It's not supposed to be in the first of the logic of real numbers, because it isn't a real number. So, well, for one thing, we don't even know that this infinitely small number satisfies the inequality itself, just even if it makes f happy. If this is the wrong kind of quadratic inequality, then really, 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 really tiny little numbers don't even satisfy it. So we also have to make sure that the quadratic inequality itself is happy with being true at an infinitely small number. That's by construction for the linear or quadratic roots that the quadratic inequality satisfies them. But it's not at all by construction for minus infinity. It's just sort of another guess of a case that could happen. And now, of course, plugging these minus infinities in again needs a virtual treatment, not a literal one. So instead of literally plugging in the forbidden, not quite real number minus infinity for x into the logical formula, I'm getting an extended, syntactically extended logical formula that we would have to make sense of. We plug in an infinitely small number virtually. So we plug it in and immediately rewrite it. And you know, here we have on the left-hand side this extended first of the logic of the reals with minus and plus infinity somehow added on to that. But on the other side, we stand completely in first of the logic of real arithmetic. We just syntactically get our way out of that. And that's equivalence really then means that the formula f is true for numbers that are sort of converging towards minus infinity, so they're getting smaller and smaller and smaller and smaller. If they're just small enough, then this is true if and only if that virtually substituted formula is true. The limit process takes care of the fact that, well, any concrete number we choose could maybe not have been just quite small enough just yet. And then the only question is, well, that's a beautiful theorem, but how do we actually define the virtual substitution and the virtual substitution lemma? How do we plug in virtually, without mentioning it, the minus infinity for x in an equation case? So if you have a polynomial equals 0 case. Suppose the polynomial is of this shape. P equals a sum with some coefficients that don't mention x times the powers of x. So ai times x power I, some combination of those. Then, well, when is this equal 0 true for minus infinity? So minus infinity, that's a really tiny little number, right? So when does that satisfy an equality? Well, because it's always very small, remember it's a rubber band number. It only satisfies an equality if all the coefficients were 0. So if all of these ai are 0, that means this is equivalent to the conjunction of all the coefficients of the polynomial being 0, because, well, if they're all 0, well, then certainly an equation is true for an infinitely small number. And again, remember, the polynomial's coefficients don't literally have to be numbers like 7, 9, 5, and 22, because they could still be polynomials mentioning the other variables, y, z, and so on, just not x. But in any way, we now have a logical formula in first order logic of real arithmetic that never mentions infinities or minus infinities, but still is equivalent to that. Whew, that was good. What do we do in the case where we're virtually substituting into a logical formula that happens to be a p less or equals 0 formula, and we're trying to virtually plug in minus infinity for x? Well, in that case, that's certainly the same as plugging it into either p less than 0 or p equals 0. And why am I doing that? Well, because p equals 0, plugging minus infinity in for that, virtually we've already defined up here. We already know when an equality is true at minus infinity. So this case is precisely the next case that we need to worry about. And then we only need to worry about it once, which is a good thing. How do we plug in minus infinity for x? That's essentially the question whether the polynomial will be negative for infinitely small numbers. How about I punt on that for now and just call the definition p of minus infinity is less than 0, which is an augmented definition, no worries, and we will define it somehow later on. And right away go to the next remaining case where we say, well, suppose we would like to plug in minus infinity for x virtually into a not equal comparison. When is p not equal 0 true at a minus infinity or an infinitely small number? Well, again, also this equality would be true as long as not all the coefficients are 0, right? It's precisely the opposite of the equation being true. Okay, that means, in other words, this is just a long way of saying, since that works for these atomic formulas, and so we can easily lift it to ands and ors in those as well, that the only case we really need to define is this case. How do you syntactically characterize whether a polynomial is negative at an infinitely small number? So is it ultimately negative as the argument keeps on getting smaller and smaller and smaller, essentially? Which is this condition, whether the limit for x converging to minus infinity of p of x, whether that's negative. Well, let's define this by cases, okay? So the easiest case, I guess, is if the polynomial is a very simple polynomial because it's a constant, right? So if the degree is less or equal 0, it should be easy. So how do we know whether the polynomial is going to be ultimately negative at minus infinity for a polynomial that really doesn't actually depend on x? Well, we just write it down itself, right? If the constant, which it then is less than 0, then, well, of course, even if you plug in minus infinity, it will be negative because the constant itself is negative. So that was easy. So by induction, we can now handle bigger degrees by assuming we already have recursively handled smaller degrees. We essentially need to peel one degree off of the polynomial. Well, how do we do that? What's dominating the behavior of the polynomial? If we have a polynomial that has, x squared and x and all kinds of degrees, then the behavior certainly is going to be dominated by the highest powers because, well, intuitively, infinities and minus infinities, power 2 is certainly going to be bigger than just power 1. So the limit in the limit process that this is performing, do the higher powers win over the smaller powers? Because with large quantities, such as approaching minus infinity, do the higher degrees always win out? So let's see. In other words, if the leading coefficient, the one with the highest power, that's negative, well, but remember that we actually, because we plug in minus infinity here, We also get the minus sign from minus infinity, sort of, and we get minus 1 power of the degree multiplied with the leading coefficient. Because, well, why minus infinity squared? That should still be a number greater or equal to 0, but minus infinity cubed, that should be a number less or equal to 0. Right? Okay, but the rest just simply depends on the leading coefficient. So if the leading coefficient has the appropriate sign, taking the sign of minus infinity into account, well, then we're done. Well, that's not the only case, right? The other case is what if the leading coefficient is positive? Well, then it's bad, because if you plug in minus infinity and we have a positive leading coefficient, it will be a very positive number, which will not make p less than 0 ultimately true. But it could still be equal to 0. What do we do if it is equal to 0? Then we need to ask somebody else, right? And then we need to ask the remaining polynomial. So if the leading coefficient is precisely 0, in which case, of course, the silly sign didn't matter a whole lot, then we ask the remaining lower degree polynomials by simply ignoring the nth power. So while the polynomial was of the shape a sum over I equals 0 to n, now we only go polynomial of I equals 0 to n minus 1, and ask the lower degree polynomial whether at minus infinity it is negative, which inductively we have already defined, because its degree here is going to be less than the degree that p has. Cool. Anyway, the point is now we have an entirely logical condition on the polynomial that is equivalent to the question whether the polynomial is ultimately negative at minus infinity, so p at minus infinity is negative, and that's precisely the question we had to answer here, and now we're done with virtual substitution. Great. Let's try that out. For example, what happens when we're plugging in minus infinity, virtually, mind you, into a quadratic inequality? First, just to understand, ax squared plus bx plus c less than 0. Because remember, that was one of the cases that we came from when plugging it in for less or equal, because that basically gave us, well, either it's equal or it's less than. So let's consider the less than case. Well, in that case, we ask whether the leading coefficient with the appropriate sign is negative. So the leading coefficient in this polynomial is a, it's the coefficient in front of x squared, and the leading sign is minus 1 squared, so it doesn't matter a whole lot. Because the square is the minus 1. Well, or the leading coefficient was non-informative, so it is 0, which again, in general, we can't know because, well, maybe this mentions other variables. But then the lower degree one is ultimately negative, and the lower degree one, again, by the same construction, will ask, is its leading coefficient negative? Its leading coefficient is b, but it now has a minus 1 power 1 because it's the linear coefficient. So it's the one in front of the x power 1 expression. So is minus 1b negative? Or is it again still unresolved? So is that leading coefficient also 0? But then we ask the leading coefficient of the remaining, now only constant expression. Now we fall into the first case because the degree of c itself is certainly 0. So we just ask whether c is less than 0. And then we take the whole thing and simplify it a little bit. For example, this apparently didn't matter, right? Here we have minus b less than 0. We might as well multiply the minus 1 out and ask whether b is positive. And we get this expression and think about it and say, actually, that makes some sense. So at minus infinity, is ax squared plus bx plus c less than 0 true? Well, whenever the leading coefficient is negative, sure, because then it will be the x minus infinity squared will be a very greater or equal to 0 number, dominating anything else. But since the leading coefficient is negative, that whole sign will tend to minus infinity. Well, or it wasn't, right? If a is 0, well, then we ask b whether b itself is positive, because plugging minus infinity in for x will be a negative number. If we multiply it with a positive number, it will also ultimately be negative. Or if that still didn't give us a sign, then we ask c itself. The constant is negative and the others coefficients were 0, then of course also at minus infinity will it be negative. And that just corresponds to the cases down here. For example, for the case, concrete one, minus x squared plus x plus 1, because the leading coefficient is negative, we have this case, and we plot the polynomial, then of course, yeah, at minus infinity. So if we keep on walking that way infinitely far, we will indeed find a negative sign. Makes a sort of sense. For example, for the case where a equals 0, but b is positive, so for this case here, for example, x plus a half, we find out that this linear function will indeed, if we keep on walking infinitely far to the left, right, so mind you, this is not connected here in a certain sense, right, do we find a negative sign. And for the case where a equals 0 and b equals 0, but c is negative, so it's actually this case here, for example, the constant polynomial minus 1, do we also find, if we keep on walking infinitely further to the left, that the sign is negative. Well, this seems to work just fine. Now, that defines for us virtual substitution for quadratic inequality solutions, linear solution, quadratic roots, or the infinitely small number minus infinity. There's other conditions to worry about, so let's just directly generalize it right away. What happens here in this first logic of real arithmetic, augmented with the minus and plus infinity, is really that we had? Well, what happens is that the ordering relation needs to be augmented such that for all numbers, even infinities and minus infinities, is minus infinity less or equal this number, and that is less or equal plus infinity. So in other words, minus infinity and plus infinity are the smallest and biggest augmented extended real. That's complete lattice because every subset now has a supremum or infimum. When in doubt, you refer to plus infinity or minus infinity. But how do you define arithmetic on this beast? Well, for example, what is infinity plus 1? Well, infinity plus 1, that also is some number, but it's supposed to be less or equal infinity, right? But also infinity plus 1 is supposed to be bigger than infinity because we just added something. So certainly infinity is supposed to be less or equal than infinity plus 1 because, hey, we added 1. But because infinity was the biggest one, also infinity plus 1 needs to be less or equal infinity. So infinity plus 1 and also infinity plus x is actually infinity. That's weird, right? Minus infinity plus x, but however is then minus infinity, so they're magnetic in a certain sense, the infinities, right? Infinity times x? Well, I guess that's an infinity at least for positive x's, right? If we multiply infinity with a positive number, it will stay infinite, even if it's a very tiny one, like infinity times 0.000001, still it's going to be infinite. But if we multiply infinity with a number that is negative, then we're going to get minus infinity, right? Because the negative one slips the sign. And in these two cases is a dual. So minus infinity times a number which is itself positive stays in minus infinity. But minus infinity times a number which is itself negative becomes plus infinity. Okay, so far this was working quite well. What's infinity minus infinity? That we also somehow need to define. I guess that's actually kind of bad. That's really undefined because, well, infinity minus infinity is of course nothing else than infinity plus the inverse of infinity. So it's infinity plus minus infinity. What? But wait a minute, right? By these up here is minus infinity the same as minus infinity plus 1, right? So here. Now we can reassociate and have infinity minus infinity and the whole thing plus 1. So this number that we're starting out to define here is the same as its plus 1 successor, and that's going to begin to be very awkward if you're not careful. Likewise, 0 times infinity. Remember, infinity times a positive or negative number we already know, but 0 times infinity? No, there's like two limit processes trying to compete for attention, right? This is a very small number, 0. This is an infinitely large number. If we multiply them, it's better to make sure they're undefined. infinity divided by infinity or minus infinity over all of these combinations. It's also better to leave this undefined. And in fact, you could say maybe 1 divided by 0 should be infinity, but it's again for structural reasons better to say that these are all undefined. So the point is, yes, first the logic of extended reals with plus and minus infinities is possible to define, and some things are sort of easy, but other things become pretty subtle, so it's better to stay clear of that and merely virtually substitute. These infinities are only needed virtually during the virtual substitution, never explicitly, only in our arguments about it. Why is it correct? Never literally when writing anything down. Now, okay, that was cool, but now let's look at quadratic inequalities that are strict. Ax squared plus bx plus c is less than 0, and some other conditions f. When does such an x exist? Well, it's a quadratic polynomial. We know the roots of the quadratic polynomial. We even know that the roots are 1 or 2 or maybe 0, depending on whether the polynomial has a actually linear behavior, so a is 0, whether it has a proper quadratic behavior, and then the discriminant tells you whether the quadratic solutions exist or don't. That's all cool, but what happens if we plug them in? So let's write it out. The solution of this quadratic polynomial, which if it really is a linear polynomial, will be the linear solution. The roots of this quadratic polynomial, if it really is a quadratic polynomial and has square roots, will be the positive and negative square root. And then there's the still minus infinity case that we virtually substituted. Well, okay, well, that's all nice, right? But if this is a strict inequality, of course, the points where the polynomial evaluates to 0 are actually the wrong one because they don't even satisfy the strict inequality. They only satisfy the weak inequality. So what do we do then? For example, in the linear case, I guess we don't need to plug in minus c over b, which is the case where these things in the linear case are 0, but we need to plug in a point slightly off of that. Just like with the quadratic roots, do we not need to plug this places where there's 0 in directly, but places that are slightly off? How much off? I don't know. +1 maybe? Well, maybe that was actually too large, so maybe plus 0.1. Well, depending on the coefficients, that might also be too large. Maybe plus 0.01. Well, you know what? They might also have been, so maybe 0.001. Or actually, you know what? Maybe 0.001. You kind of get it. No matter which number I write down, these will not quite be small enough. We need to plug in a number that is really tiny, because the square root solutions will not make the strict inequality true. Only points that are slightly off will make it true. But no matter which concrete number I plug in for epsilon, it might have been just a little bit too big. So the point is, epsilon, again, is a rubber band number, one whose magnitude, whose absolute value, is always smaller compared to any number that's a real one on any comparison. So whatever number you're trying to compare this epsilon to, it just automatically shrinks a little bit and says, I was really a bit smaller than you thought I was, in order to make sure that the coefficients that we have here in the polynomial and its quadratic solutions and so on aren't incompatible with the epsilon. So what is this epsilon? It's an infinitesimal, right? It's really, really tiny. And the point is, again, that while this sort of, yeah, I guess is the right solution, but it's the right behavior in a very, very, very extended first order logic with infinitesimals. And the point is that plugging in these infinitesimals into the logical formula literally is equivalent to plugging them in only virtually with a virtual substitution we're about to define, where this here leads to non-standard analysis, which is first order logic of the field of the reals extended with these infinitesimals epsilon that are just smaller than any positive real number on any comparison. And that side is just vanilla first logic of the reals, just rewritten away appropriately. So in other words, the formula f itself is true in a state where we replace the value of x with a value r that is converging to e from the top, so it's getting closer and closer and closer to e, if and only if the right-hand side formula is true in the original state. So this is virtually substituted one where we sort of pretend substitute e plus this impossible infinitesimal into it. So what are these infinitesimals now? Well, this is the non-standard field extension of the reals with infinitesimals, but as soon as we add infinitesimals, we also have to like add in what does an infinitesimal plus an infinitesimal mean, what does an infinitesimal times an infinitesimal mean, all kinds of things. What are these infinitesimals? They're always as small as needed. Remember, they're rubber band numbers, so an infinitesimal is positive, but it's smaller than anything else that's positive. So for any other proper real number that you compare it to, if x is a positive number, then epsilon says, I'm actually smaller than you think I am, no matter how tiny the positive number is. Epsilon is always a bit smaller than that. Now, this changes everything because, for example, the standard reals satisfy the Archimedean property. For any number that is 0, that is a real number, if you just add it often enough, it'll exceed 1. That means for every real number that isn't 0, is there some number of times that if you add the number to itself that many times, and then take the absolute value, you do get a number that exceeds 1. Archimedean property says even tiny things, if you add them up enough, they'll exceed big things. But that's very different for the infinitesimals. So the reals with the infinitesimal added on to them are non-Archimedean. Why? Well, because even if you add any natural number of times this infinitesimal to itself, will it still be smaller than 1? So that's the non-Archimedean property that says there are things that are so tiny that no matter how often you add them to themselves, a natural number many times, do they still not account for anything? Well, in what sense are infinitesimals? Inverses of infinities, and to some extent you can imagine them like that, right? So maybe an infinitesimal times an infinity is 1, so it's the inverse of that. Well, but maybe also the negative infinitesimal times a negative infinity is 1, but that's awkward, right? Because what happens then is the infinitesimal plus 1 times infinity plus 2, is that then also 1, or is it something slightly different? So that's complicated, right? Also, if you have all these expressions, how do you order them? For example, if you have epsilon square compared to epsilon, compared to x square plus epsilon, compared to x plus epsilon square, compared to x squared plus 2 epsilon x plus 5 epsilon plus epsilon square, then, well, in fact, they're all ordered in this relationship, right? But it's already difficult to figure all of these out. The point is, we don't even literally need these infinitesimals, rubber band numbers. We just need them for inspiration in order to define them away by virtual substitution. Infinitesimals are only needed during the virtual substitution quite virtually. They're not really needed, and they're never needed explicitly in what we do. So how do we then plug an off-root, so an infinitesimal addition to an actual square root expression into a logical formula virtually, so by rewriting it right away? Well, there's a bunch of cases. Equality less or equal less than not equal 0. For a polynomial that is a sum of coefficients that are other polynomials and other variables, not x, times powers of x. Well, so when does an off-root e plus an infinitesimal satisfy an equation p equals 0? it sort of almost never does. Why? Because whenever you take this rubber band number epsilon and plug it into p equals 0 and it says, yep, I'm a root, then remember it's a rubber band number, so it really is a bit smaller than you thought it was. It just shrinks as you're looking at it essentially, which means it just shrank and is now off root. So for an off root to satisfy an equality, that's essentially impossible except when the equality was stupid. So except when all the coefficients of the polynomial are 0, which is a logical formula. In that case, that's the only case when even the infinitesimal plus epsilon can wiggle its way out of having satisfied p equals 0. But it's a very special case. Okay. How do we virtually substitute an off root, e plus an infinitesimal, into a weak inequality, p less or equal 0? Well, we do the same trick as before. We punt on that and say, well, that's true if we substitute it into p less than 0 virtually, which we define in a moment, or we substitute it into the equality, which we have already defined up there. Very nice. So how do we then define that p less than 0 is true at an off root e plus epsilon with an infinitesimal epsilon just by virtually substituting it in? Well, we again punt on that for a little while and define whether p is immediately negative at x. So just a tiny bit right of x is p negative, and if we have a definition for that, then we also have a definition for is it true at virtually substituting the original square root e in for x in this definition, and have then reduced the question whether at a point just right of e, so e plus epsilon, is p less than 0 true by asking, well, just right of x is p 0, which we will define down there, and then virtually substitute into that, well, instead of x, we actually want e as the base point for that. So, but before we could actually define that, let's first finish off with p not equal 0. When is that true after virtual substitution? Just like an equation is almost never true at an off root, and not equals is almost always true, except in very stupid disequalities, which are the ones where none of the coefficients is non-zero, because well, then not even the wiggling around of the off root epsilons have a chance to make this true. That's precisely the opposite of that. Now, let's define this question. Remember, in order to ask whether p is less than 0, just right of e, we substitute this original square root for x virtually in this expression, which is asking whether p is immediately negative at x, which means as y is converging to x from the right, so it's really close to it, is p of y negative. Well, how do we do that? Again, we will do this inductively. So if this is a very simple polynomial with degree 0, that's very easy to do that. So if the degree is less or equal 0, we define it in one way, and if it's of larger degrees, we define it by induction on that. If it's a constant polynomial, then is it immediately negative at x? So just right of x is it negative? Well, that's just whether it is negative, because if it is currently negative, because it doesn't have a variable x occurring at all, has degree 0, or less than p less than 0 precisely is the equivalent to that. Now, in the other case, if variable x actually occurs, well, then we have to be a bit more clever. Then what is determining the behavior right next to x? Well, let's see. So if p is presently negative at x, then of course it also will still be presently negative just immediately after x, because, well, x doesn't change that quickly, right? Remember, we're in the business of actually defining what it means to add an epsilon infinitesimal to that. That doesn't move so far as to touch a root. So if p is less than 0, then p will still be immediately negative at x, because, well, by continuity, we don't drop from negative, increase to 0 without having moved a bit of a distance. But if that's not the case, right, if p is actually 0, then there's still another case where it would be immediately 0, even if you're presently at a root, namely if the trend is going downwards. And how do we ask the trend? Well, better do it in terms of a lower degree polynomial, otherwise our inductive definition won't work. But who do we ask for if in need of a question, what's the trend at a point where it happens to be 0? We ask the derivative of the polynomial. So the derivative of the polynomial, and ask that, dear derivative, are you immediately negative? 0. And the derivative of a polynomial, remember, will of course have lower degrees, so that's actually well defined because we're defining immediate negativity at a degree p polynomial by reducing it to immediate negativity at a degree p minus 1 polynomial at most. So we break ties by successive derivatives being immediately negative at the root of p, and then plug it all in. Let's see an example of that, right? So immediate negativity is the key notion. And for example, if we ask, is ax squared plus bx plus c immediately negative? Then, well, it is immediately negative exactly by this definition if it's presently negative here, or it's presently 0, but the trend is negative, and the trend is the derivative of this, right? So ax squared plus bx plus c has a derivative 2ax plus b, and if that's negative, right? Again, we recurse into this. If it's negative, then, well, because the first derivative is negative, we know. Or if that first derivative is still 0, right, then we ask next derivative. Next derivative of 2ax is, of course, 2a, and now we're in the base case where we have a degree 0 polynomial, and so we just leave around whether 2a is less than 0. Cool. Having done so, remember that we use this auxiliary definition in order to define what it means to plug an off root, so just right of the real root of the polynomial into it, by asking, let's plug the actual square root into the immediate negativity, which we just computed up there. So here it is, and we plug the literal square root into this immediate negativity expression, which, well, remember how the virtual substitution works. We plug the square root that solves this equal 0 into this less than 0 question. So of course it will have to come out now. We plug the root into an equal 0 thing for its own quadratic polynomial, so that of course will have to come out with a yes. Then we plug it into here. Well, that's more complicated to see, but here essentially is what happens if we plug it into 2ax plus b. Here's what happens if we plug the square root expression for the quadratic polynomial and the linear polynomial. That will happen to be 0 equals 0, so true. And here's what happens if we plug it into the 2a less than 0 case, but just, of course, just 2a less than 0 because, well, x doesn't even occur, right? If we take that and simplify it, for example, this is impossible, that's just true, so we can skip it. This is impossible. That's impossible. That's always true, but it starts with a conjunction, so that can also be skipped, and things like that. Then we end up with this expression. Now that can be simplified a bit more because 4a squared less or equal 0 is simplified to just be a equals 0. It's easier because of lower degrees. But then if a is 0, we can plug this value in for 4a squared as well. So that's 0 multiplied some other things less than 0. That's very easily seen not to book out. And so the only thing that's remaining is 2a less than 0, which is precisely the outcome at the end of the day. And that makes some sense because a quadratic polynomial at its slight off-root will be less than 0 just whenever the leading coefficient is negative, because then it will be negative. So let's write down the cases. This is a concrete case, minus x squared plus x plus 1, where a is less than 0, where it's minus 1, right? And indeed, just right off the positive root, which we have plugged in here, is it negative. This is x squared minus x minus 1, so of this shape, where a is positive. So indeed, just right of the positive root will it not be negative, but just right of the negative square root will it have been negative. Just didn't compute that up here. And here we have, for example, minus a half x squared plus x minus 10, also in this case, just right of the positive root. is it going to be negative? So this works really well. Now remember, we're in the process of defining virtual substitution for quadratic strict inequalities, and we did so by making sure we don't have to literally work with infinitesimals that we substitute into formulas, which is even more scary than literally substituting in square roots and divisions, but we just virtually do so by way of the virtual substitution lemma. But now let's summarize it all up. Let's do once and for all of quantitative elimination by virtual substitution of any quadratics. If we have a formula f in which all the atomic formulas are of a form quadratic, so ax squared plus bx plus c compared to 0, where, yeah, it's the proper shape, so x shouldn't occur in ABC because that would be cheating, that wouldn't be literally of the quadratic form. And the comparisons of the atomic comparisons that are supported here, of course, others are just like that, where all of the atomic formulas are most quadratic in particular, is what that means, or linear or constant, where the discriminant is b squared minus 4ac. Just to abbreviate the notation, then there is an x such that f is true if and only if, we've already seen it, either f is true at a really, really tiny little number, minus infinity, that's where these inequalities help, or, and now it depends, for the weak inequalities or the strict inequalities, for all of the ones we find in the formula f, do we write down its characteristic behavior. So if it was really linear equation or linear inequality, so a equals 0 but b wasn't, then we plug in the linear solution. Or if it was properly a quadratic one, so a isn't 0, but the discriminant, look, b squared minus 4ac that comes out of that, says that a solution exists at all, then we plug the positive or negative square roots into this. So exactly minus b plus square root of this d over 2a, or minus b minus square root of the d corresponding to this over 2a. In other words, for a weak inequality, in addition to the minus infinity cases, do we plug in the linear and the quadratic positive or negative solutions, depending on which case we're in. If we can't make up our minds, then we leave both the a equals 0 and the a not equal 0 around logically. That was for the weak inequalities, where the actual roots are the right solutions. Now for strict inequalities, we can't do that, but we plug in off roots. We plug in a point that's an infinitesimal way from the linear solution, and we plug in points that are an infinitesimal way from the positive and negative square roots. Again, virtually next to the expressions. And the equivalence really needs the roots and off roots from all of the atomic formulas you find in F. Now, what do we do with equations and disequalities? Well, equals 0, that behavior is what we already started out with, is essentially the same as the behavior of lesser equals 0, except that then minus infinity plugging in won't actually end up working very well, but that means we can add it into the lesser equal case. We can write down an equal as one of the cases we consider here as well, and the not equal. Well, the roots certainly don't satisfy the not equal, that was easy enough, but we also can cover the not equals as part of the strictly less thans in the condition as well. So now we have the actual virtual substitution theorem for inequalities that says there is an x such that f is equivalent to a bunch of cases. Really small numbers, or the linear or quadratic roots, or the linear quadratic off roots with infinitesimals added into this. And all of this, of course, needed the virtual substitution lemmas that said plugging in square roots and divisions literally is equivalent to plugging them in virtually to make sure we stay in first the logic of real arithmetic. Plugging the minus infinities in literally is equivalent to plugging them in virtually just by rewriting right away. And plugging the off roots in literally is equivalent to plugging them in virtually so that we stay in first the logic of real arithmetic. Notice in principle there's also alternative formulations. We've worked with sort of minus infinity very far to the left, and all the roots of the polynomials respectively the off root, so slightly to the right. Right? Alternatively, we could have rephrased everything to have the positive infinity in all the cases slightly left to the square root. So we would have had e minus an infinitesimal into plus infinity to cover all the cases by having plugged in not just the square roots or linear roots or whatnots and so on, if at all applicable, and the slight off roots to the right and the minus infinity, but also have covered all the cases in the other way around. In principle, those two formulations are the same. We might as well choose the one we've seen. In particular, the point is also that even if one polynomial doesn't select the appropriate roots because it wasn't its roots, no root can be rejected without being mentioned by another polynomial, nor can any off-roots be rejected without another polynomial being there that has different roots and will thus generate more roots. By the way, notice that generalizations to quantified elimination of higher degrees also do this kind of thing. They place sort of representative points into all of those intervals. But it does then become more complicated because you cannot just write them down of nested higher root expressions, for example. So you need to look at derivatives and relationships of derivatives to figure it out appropriately. Why is this theorem a theorem? Why is it correct? Well, one direction is really easy. This is a by implication. The direction that says these guys imply that guy is really easy. That just follows from the virtual substitution lemma with the extended term witnesses, because essentially we plug in concrete points, and if f is true for any of those concrete points, I guess there is an x such that f. Well, here we virtually, which is equivalent to literally, plug in square root points. Here we virtually, which is equivalent to literally, plug in linear solutions, and here we plug in virtually, which is equivalent to literally in minus infinity points and off epsilons and so on. But you know, they all correspond to certain real numbers at the end of the day, even if sometimes after limit processes. So the implication from right to left, really straightforward. But the hard direction is, of course, that if none of them was true, that there couldn't have been another point that would have done it. So the implication from here to there is the hard one, the one that isn't just based on the witness, but the one that says if it isn't one of those, there isn't another witness either. Is that true? In a proof sketch, please look at the textbook for a much more elaborate proof, that this equivalence is valid if and only if it's true in every state. Okay. So there's fixed and arbitrary state, and then arbitrary state, do of course all the other variables have concrete real values, which means there's only one variable remaining. Everything else already has a concrete real numeric value. And now, by a property it's called ominimality, the solutions of these polynomial conditions form a finite union of disjoint intervals, because, well, now we have a univariate polynomial, remember, right? We only have one variable and one polynomial, and one variable only has finitely many roots. Well, f could mention multiple of them, but even finitely many polynomials in one variable only have finitely many roots. Now, without loss of generality, we have moved the interval endpoint such that they exactly correspond with all the roots, because all the polynomials are quadratic in f, which was one of the assumptions of the virtual substitution theorem for quadratic polynomials, can no other roots actually exist. And all the side conditions that you have here, for example, the discriminant not being a negative, and the polynomial actually being a quadratic polynomial, or the polynomial actually being a linear polynomial, are exactly the ones that have to be met, otherwise there can't be a solution just by properties of mathematics. That's precisely what the discriminant meant. And then, whenever you have a non-point interval, right, then it also does contain the epsilon offsets, because, well, this rubber band number is always a bit smaller than whatever endpoint we could have chosen. So whatever is the next endpoint for the polynomial where one of the polynomial changes signs, the epsilon is always just small enough to fit into this. This is the proof sketch of intuition for this. Let's use it. For example, Remember that we have already shown that for a quadratic equality, and the question, does it have a non-negative root, which is what this existential quantifier is equivalent to, is this the answer? Okay, that was the computation symbolically that we've done last time. Let's just simplify this by plugging in -1, remember, b square. If we choose -1 for b and 1 for a and leave the c symbolic, right, then we have here -1 square -4 times 1 times c, and the rest simplifies sort of like that, and here's some redundancy in it. So the only remaining thing is this condition, and of course the c greater than or equals 0 or c lesser than or equals 0 or some other stuff is all equivalent and just true. So there is an x such that x squared minus x plus c equals 0 and x squared equals 0. So in other words, x squared minus x plus c has a non-negative root if and only if 1 minus 4c is greater than or equals 0. That's what we did last time already, just in this particular concrete instance. Let's do the same thing with a lesser equal. Well, in that case, we plug in still the quadratic roots of this quadratic polynomial, right, which will give us this condition, right, except we also plug in it could be true at minus infinity, which it will turn out it isn't, because, well, why? Well, the leading coefficient is positive, and so if you plug in a really negative number, and for x, of course, this won't be less or equal 0, this will be bigger or equal 0. So this will end up coming back with a false, so that doesn't give us any new behavior. And remember, in the theorem of virtual substitution, we leave the disjunction of all the solutions of all the polynomials, including also that polynomial here, right? And from that polynomial, x, the solution is, of course, well, guess what? 0, right? And if we plug in 0, that will solve that side. 0, whether it will solve that side depends on the sign of c, but the point is, this will give us back precisely whether c is less or equals 0, and c is less or equals 0 is already subsumed in this condition, because this condition is equivalent to 1 is greater or equal 4c, which is equivalent to 1 over 4 is greater or equal c, which implies that if c is less or equal 0, well, then that condition is also true. So this just is all deleted. In other words, in this particular case, in the inequality case, do we get more computations but not actually any different set? The solutions of this quadratic polynomial already tell us everything there is to say about it. But there's other cases too, and here's one. What if we start the same way, but then we have another conjunct, a conjunct that says n minus x plus 2 is 0? Well, then the quadratic roots that we get from this polynomial here aren't going to do it for that. And that's where it is important that virtual substitution theorem leaves around the disjunction of all the roots of all the polynomials we find in here, even if it wasn't important in that case. So first of all, we start out by asking, well, what if we plug in minus infinity as a number virtually, of course, never you mind. And we have already seen that the first conjunct isn't even happy with that, so the others can't be more happy about it, because the conjunction won't be. So that will give us a false, just as in this case up here, right? But now the point is that even if the quadratic root of x squared minus x plus c less or equals 0 have made this and this polynomial happy, so these two here will be happy, the quadratic roots of that polynomial will not make this minus x plus 2 equals 0 equality true, because that would require, well, if you compute it, 8 minus 4c to be equal 0, but that means c has to be 2, right? And if c is 2, then it's really, really hard to satisfy this, because remember, that's an upper bound on c, that's 1 over 4. So this would give us false in this particular case. The quadratic root from this polynomial wouldn't do it. So it's good that we don't stop there, because there is a solution. The other root we get is from this polynomial. So we select this polynomial and ask what's your root. That's, of course, the solution 0. Never mind square root divisions and square roots and divisions for this. we just plug in 0 literally because that's easier, right? But if we plug in 0 literally, then at the latest here, 0 plus 2 equals 0 will not actually be true. So that also comes back with a no, right? So we already figured out that this is no, that this is no. Fortunately, we've got one more case remaining, namely, we also plug in the root of what happens if we select the last polynomial, and that has a solution too. And, well, let's see. If we plug in the solution 2 into this equality, well, of course it will be very happy. It's its own solution. 2 will also satisfy greater or equal 0, right? 2 is greater or equal 0. And now it comes down to that. 2 square minus 2, well, that's 2 last I computed, plus c is lesser or equal 0. So the question is entirely equivalent, because that's satisfied, to just the condition 2 plus c lesser or equal 0. In other words, whether c is lesser or equal minus 1. Whether c is lesser or equal minus 2. And it is very important for this theorem to work, as you see here, that we considered all the roots of all the polynomials. You also see that it's very important to simplify things away as early as possible, right? This was already simplified to false as quickly as possible, and it was also very important that up here, when we're computing these polynomials, that we simplify right away. Let's summarize. What we've seen is the virtual substitution theorem for quadratic equations. So when we have ax squared plus bx plus c equals 0 and some other conditions, then we can directly substitute it in. This is very nice. We don't end up with a big disjunction of all kinds of other roots, because if an equation has to be true, well, whatever solution it is that we're talking about, it has to satisfy this equation. So that means we plug in the linear solution virtually whenever it was actually really just a linear equation, because the leading coefficient was 0, and we plug in the positive and negative quadratic root solutions from that. Well, of course, only under the conditions that they are actually existing, so the discriminant condition is true. That was very easy and very good. We've seen it last time already. Nice thing also, here we only get out multiplications, so the degrees don't increase. Here we just get out squares, so in a sense the degrees also don't increase. A very nice case. It was boiling down to the virtual substitution limit. It says literally or virtually substituting square roots into it are equivalent formulas. Just these stay first to the logic of reals. Now we've also seen how it generalizes to the presence of inequalities. If we don't have an equation as a conjunction in the quadratic elimination conditions, and we have to work with the inequalities. And in that case, well, it's a bit more complicated, but if all of the formulas that are atomic in F are quadratic or linear or maybe constant inequalities, so they'll summarize the quadratic case, then there is an X such that F is equivalent unconditionally to it either being true at minus infinity, which we virtually substitute in, or for all the weak cases, so equality or less or equal 0 conditions, at the linear or quadratic roots, depending on whether it was actually linear or quadratic, or for all the strict cases, so the strict inequality or the disequality, at all the off roots, so compute all the roots of the polynomials, the linear or quadratic ones, and virtually substitute in a point that's just a tiny bit further than the actual square roots in order to make sure that there is a chance for the disequalities or strict inequalities to be satisfied. Also notice that unlike in the virtual substitution equation case, where the equation is satisfied by construction, so only the remaining f needs to be virtually substituted. Also nice, we deleted something. In the virtual substitution for quadratics with inequalities, do we have to keep the entire f around, so including the original conditions? And the virtual substitution lemmas make this correct. The ones that imply that literal and virtual substitution of square roots and divisions are equivalent, literal and virtual substitution of these infinities are equivalent, and literal and virtual substitution of infinitesimals are equivalent. What you've seen overall is Tarski's miracle, that first the logic of real arithmetic is decidable, although admittedly we only looked at the quadratic cases. The treatments for other cases are admittedly more complicated, but follow in spirit very much what we've seen. There's an algorithm that decides whether closed formulas, so the ones without free variables, all the variables have already been universally quantified, to be valid or not. And also, quantitative elimination, which is the working horse for that, computes quantifier-free equivalence. So even if we're not trying to decide, we can tease out conditions when it would be true, which is useful for proving as well. It all works by successively eliminating quantifiers, not just by deleting them, but by rephrasing them equivalently. Quantifier elimination accepts three variables, which give equivalent conditions that identify the requirements for truth, which is a beautiful synthesis technique. Virtual substitution that we've seen does also work for quantifier eliminations for degree 3 by equivalent syntactic rephrasings of the semantics, but at some point virtual substitution alone can't quite handle it because we cannot write down the solutions of these higher degree polynomials. For example, a general polynomial of degree 5, we cannot write down the solution with any number of root expressions, for example. Quantifier elimination does proceed inside out. In particular, the degree needs to be bounded by at most 3 on each of those iterations, and that's also where equations are better because they don't blow up the degrees. There's also optimizations. Look at the textbook. And speaking of optimizations, important fragments of arithmetic do permit a fair number of optimizations, not just during the simplifier that's super important during virtual substitution and other arithmetic techniques, but also by just working in very different ways. In particular, also, universally quantified weak inequalities or existentially quantified strict inequalities are easier because they all boil down to infinitesimals and infinities, and they just never satisfy any equality except in extremely degenerate cases, which you can prevent by appropriate assumptions. So they're easier to handle because they don't have all those complicated cases anymore. So rephrase your question in arithmetic to make sure you fall into this fragment, if at all possible. Cylindrical algebraic decomposition due to Collins works for any arbitrary degree, and partial cylindrical algebraic decomposition due to Hong and Collins a bit later on, 2 decades later, also works in pretty efficient ways for any arbitrary degree, but it can't be arbitrarily good because, well, it's a miracle after all that real arithmetic is decidable. In other words, the takeaway lesson for you is that you should be simplifying the arithmetic to the relevant parts, using your structural insights about the kinds of questions you would like to show about your cyber-physical system, and then transform them to make it all fit back together.